Hi, good day to you all. Welcome to another chemistry class. So today we'll be talking about orbitals and shells. Orbitals and shells. So in chemistry, it's not only in biology you hear of shells. We also have shells in chemistry. So now, what are these orbitals and what are these shells? What are their uniqueness? What are their usefulness? And why do we actually need them? Now, if you want to write any electronic configuration of a particular element, you might be told to write it based on the number of shells and the number of orbitals. Now, am I still speaking in tongue? If you're talking about orbitals in chemistry, we'll be mentioning something like S, P, D, F. S, P, D, F. Now, these s orbitals can only accommodate 2 electrons. The p orbitals can only accommodate 6 electrons. The d, 8 electrons. The f, 10 electrons. These are the maximum number of electrons each orbital can accommodate. Now, when we're talking about shell, we are talking about K, L, M, N. This is the first shell, second shell, third shell, and the fourth shell. Now, why I left this place blank is because I want us to calculate it together. Now, this is the first shell. We have our formula, 2n squared. So if this is 1, so that would be what? 1 squared, 1. 1 times 2, 2. This is the second shell. 2 squared, 4. 4 times 2, 8. 3. 3 squared, 9. 9 times 2, 18. N is 4. 4 squared, 16. 16 times 2 is 32. So all these are the number of electrons each shell can accommodate. The number of electrons each of the shell can accommodate. Am I making myself clear? We have orbitals, we have shells. These are usually involved in the writing of the electronic configuration of an element. You make use of orbitals, you make use of shells. You make use of shells when you're writing electronic configuration. Now, it will be incomplete for me to just go straight to electronic configuration without talking about the half-bow principle. Half-bow principle. Now, this is how it is written. 1 hertz, 2 hertz, 2p, 3 hertz, 3p, 3d, sorry. This should be 3d, not 4d. So, 3d. So we have 4s, 4p, 4d, 4f, 5s, and so on and so forth. So based on this half-bow principle, sorry, let me adjust the lens. Based on this half-bow principle, we can easily write it like this. We started with 1s. 1s, can you see? Followed by 2s, 2p, 3s, 2p, 3s, 3p, 4s, 3p, 4s, 3d, 4p, 5s, 4p, 5s, followed by 4d, 5p, 5s, sorry, 4d, 5p, 6s, 4f, 5d, 6p, and 7 hertz. So in writing electronic configuration, it's a pity that we might not need all of this when we are writing electronic configuration of the first 20 elements. But because we have a lot of elements in chemistry, so it's better you know this principle and its arrangement of these orbitals. Now I want you to know that this 1, 2, 3, 4 being written as coefficients are the number of shells. So this is telling us that this one occupying the first shell, this one the second shell, this one the third shell, this one the fourth shell, third shell, fourth shell, fifth shell, and so on and so forth. So that is where half-bow principle comes to play in the electronic configuration. Now, out of the first 20 elements, I brought out some elements. Which is hydrogen. Hydrogen is just what? 1. It has atomic number 1. So if you want to write the electronic configuration, it's going to be what? This one will start at the first shell and what? First orbital with electrons with just 1 electron. Sorry. You know S can only accommodate 2. So we write 1. So now that this one is 6, which is carbon, let's start. The first shell, 1s2. Looking at half-bow, after 1s is completely filled, the next one is 2s. So let's go. 2s2. Once 2s is completely filled, the next one is 2p. So that will be 2p2. By the time you add up all these electrons, it should give you your atomic number. Yes, if it doesn't give you your atomic number, then there is a mistake in your electronic configuration. Let's go to 7. So 7 will be what? 1s2, 2s2, 2p3. 8 will be what? 1s2, 2s2, 2p4. 10 will be what? 1s2, 2s2, 2p6. Now, looking at half-bow principle, after 2p, the next one is what? 3x. So p can only accommodate 6 number of electrons. So we can't go ahead and say 1s2, 2s2, 2p7. No, it's not possible. You can't have 2p7 because p, which is the p orbital, can only accommodate 6 electrons. So here, after this, we now have 12, which will be 1s2, 2s2, 2p6. Now you move to the third shell, 3s2. By the time you had all these electrons, to give you 12. Sorry, I'm only trying to manage the board. Aluminium. Let's go. 1s2, 2s2, 2p6, and 3s2. You can write 3. Yes. That's why I said and. I know some of you will say 3p, 3s3. No. S can only accommodate 2. So you can write 3s3. So you move to the next one. According to half-bow, after 3s we have 3p. That will be 3p1. Good. So all those things are interwoven. All those things are what? Interwoven. S can only accommodate 2. P can accommodate 6. So you have to monitor the number of electrons these orbitals can accommodate. You have to monitor them. Or else you just continue writing electronic configuration that is out of reach. Yes. So look at 17 now. We have 1s2, 2s2, 2p6, 3s2. Now, remember I said P can accommodate 6. So by the time you add up those together, we still have 5 left, which is 3s5. If you add it up, it will give you 17. Let's go ahead. 1s2, 2s2, 2p6, 3s2, 3, this is 18, 3s6. Good. Am I communicating? Okay. Now let's go to potassium. It's 19, 1s2, 2s2, 2p6, 3s2, 3s, sorry, this should be p, 3p6. Why am I writing s here? 3s2, 3p6. Now this is 18. We have 1 left. You can't write 3p7 because p can only accommodate 6. According to half-bow, you move to the next one, which is 4s1. Now let's go. Calcium. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. Good. Now we have successfully and accurately written our electronic configuration. Is that taken? Always take notes of your orbitals and the shell. That's the most important thing. To know the number of electrons each can accommodate. After which you can go ahead, look at the atomic number and write the electronic configuration. Alright? In the absence of any question, we'll continue our class later. Bye.